In mass production, we cannot manufacture any part dimension with zero variation. That means every dimension on the part must be allowed to vary within the given allowable tolerance, and yet we must meet the given function of the part. Now the function could be required clearance or required interference or required overlap, or just to ensure the parts assemble readily with each other in the worst case. Now imagine if dimensions in mating parts are manufactured to extreme ends of their tolerances, will the mating parts still meet those functions? And how on earth we supposed to know if we are achieving those functions or not? And that's where, my friends, tolerance stackup analysis comes into the picture. So if you are new to the tolerance stackup analysis, I have created a video to explain stackup analysis from the scratch and also explained it with the example of spacer. I would recommend it to watch that video before you jump into the assembly stackup analysis. I have attached that link of the video in the cards at the top. My name is Kevin Kutto, and in this class we are going to study how to perform worst case tolerance stackup analysis in assembly. If you get real value out of this channel, consider liking and subscribing and help me in bringing more knowledge videos for you. In our example, we have got a big container and there are three small containers which are stacked side by side. Now as we see, we still have some more room to stack the fourth smaller container. Now here is the catch. I have already designed the fourth container and I really want to ensure whether I will be able to fit that fourth smaller container in this remaining gap or not. The only challenge here is every container is allowed to vary within their own tolerances, and that means all those variations are also going to affect this gap here, in which my fourth smaller container will be stacked. So now the question is, with all these tolerance variations of all the containers including this bigger container, will I be able to fit the fourth smaller container or not? And that is objective of this stackup analysis. So stating objective of the stackup analysis is the first step in conducting the entire stackup analysis. Now as you see, I have shown an arrow with dot on one side and the arrow on other side. Now dot shows the starting point of my stackup analysis, whereas arrow shows the end point of my stackup analysis. I have also defined these ends as A and B so that I can name this gap or clearance like gap A-B. If I have to fit the fourth smaller container in this gap A-B, what I am really interested is to find out the minimum gap between A and B with all the tolerance variations where I can fit the maximum size of the fourth container. So that means if I compare the minimum clearance or minimum gap A-B with the maximum size of the fourth container, I can very well verify whether the fourth container can be placed in this gap or not. So that is the objective of the stackup analysis. So let's define the objective: to find the minimum distance between A and B in order to fit the additional block or fourth block. The second step is to define conditions or assumptions of the stackup analysis. Like, we assume that all the parts are assembled at the room temperature and they meet their given tolerances and there is no wear and tear or deflection of any of the container. We don't have any unusual conditions which can affect the dimensions and tolerances of the parts or containers. If any part is subjected to deflection or excessive wear and tear, we must specify it and probably mitigate that in our stackup analysis as well. So now that I have defined my objective, I need to decide whether one-dimensional analysis in the Excel format is sufficient to perform the stackup analysis, or the part's 3D variation or three-dimensional variation plays the crucial role in the stackup. If three-dimensional variation plays the role, then we might have to use 3D analysis tools like CTOL. In this example, gap A-B is all driven by container variations in the horizontal direction, and that means it's perfect case for one-dimensional analysis. And that's why we are going to use 1D analysis for analyzing this clearance or gap A-B. And this is our third step of stackup analysis. Now, in the fourth step, we bias all small containers in such a way that they end up touching each other and create the worst case for my objective. In our case, we have fixed a big container here and then moved all the smaller containers towards the left until they touch each other and can't move anymore, and that creates a gap in which I want to place my fourth container. This process of moving the parts in defined manner is called as biasing. Now, before we move forward, I just wanted to let you know that you can learn and master in-demand design skills from me and my team at Design Gigs. We offer plastic and sheet metal domain-based trainings in which you learn all critical design skills in depth and gain confidence to deliver a functionally working design from scratch. In case your company needs these trainings, you can also approach us for corporate trainings as well. Visit our website www.designgigs.com for more details. Now let's continue with our next step of assembly stackup analysis. Once we bias the parts, we need to define the direction of the stackup. For the simplification purpose, we generally follow left to right or bottom to top convention. That means starting point will be either at the left side or at the bottom side based upon whether we are conducting stackup analysis in horizontal or vertical direction. Again, if you choose otherwise, it won't give you any different results. But if you don't have uniform practice, it could cause confusion in interpreting the results. Now, as you see, the direction from start to end is shown positive and opposite direction is shown negative. So in interpretation perspective, positive means clearance and negative means interference. This positive and negative convention is shown at the start point with the dot and arrows pointing in both the direction. That is our fifth step of stackup analysis. In the sixth step, let's define the measurable target. In our case, maximum size of the fourth smaller container is 12.5, and that means in order to fit the container, the minimum gap between A and B must be at least 12.5 or more than that. So that is our measurable target of the stackup. The seventh step is to build a dimensional chain of the stackup. You can compare the dimensional chain of the stackup with a chain in the bicycle. Even if a single link is broken in the bicycle chain, it won't work. So just like that, stackup chain also needs to be complete without any break. Chain begins from the start point and it ends at the end point. So in our case, it begins at point A and then it ends at point B. Each link in the stackup is equivalent to a dimension and tolerance. So each next dimension in the chain must begin where the previous dimension ends as per the engineering drawing. Also, the chain must consider only those dimensions and tolerances which contribute in our stackup analysis. Now, for example, in this case, since our gap A-B is horizontal, it doesn't make sense to include vertical dimension of container into the stackup analysis since they won't contribute into the gap. Also, the stackup chain must include only those dimensions and tolerances which generate absolutely shortest path to travel from point A to B. So we have to find only those dimensions and tolerances in the chain which will help us to reach as early as possible to point B. That means it is the shortest possible dimensional chain. We need to include only those dimensions and tolerances in the stackup chain which are provided on the engineering drawing. And the reason is, if the dimension or tolerance is not added to the engineering drawing, it can't be measured or controlled. Now, what happens if any link or dimension is missing in the engineering drawing? That means that dimension or tolerance itself is not provided on the engineering drawing. That's where we have to collect dimensional data from the manufacturing process. That process should be statistically stable process and study actual variation in that statistically stable process for that dimension and then include that into our stackup analysis. Or If that is not possible, get that dimension added into the engineering drawing. We cannot just take uncontrolled dimension from the CAD model and add that into our stackup. In assembly stackup analysis chain, we can switch from one part to other part through common touching point or common line contact or common surface contact in the case of bias. So as we already know, we have biased all this container to the left side. That means we have common surfaces between the parts. So we can switch from one part to other part through these common surfaces which are touching each other. So with that understanding, let's build the chain for our tolerance stackup analysis in this example here. So the first dimension will start from the starting point, which is starting point A. So let's begin from our starting point A, and my next destination will be a common surface. From this common surface, I can switch from this part to the next yellow part. So the first dimension which is contributing here is 18.5 minus 0.5 plus 1.5, which helps me to reach here, and that is my first contributor into the chain. I have shown that as negative as per this convention. So as you can see, dimensions from right to left are shown negative and dimensions from left to right are shown positive. Since this dimension is flowing to the left from the starting point, it is shown as negative. So now I reached here. From this point onwards, I have to reach to this end. So there are two dimensions which are contributing here. 15.5 plus minus 0.5 and 18.5 plus minus 0.5, and those are my second and third contributors. Both are negative again because they are moving from right to left. So now I reach to the destination which is common surface. Now I can move from this part to the yellow part. In the yellow part, the next contribution is 18 plus minus 1, which will help me to reach to the next common surface, and from there I can jump to the next part. So that is my fourth contributor. Again, it is negative as per the sign convention. Now from here, I have to move to next common surface, which is this common surface, and the dimension here is 15, 0 plus 1, and that is my fifth contributor. Again, it is minus. Now there is no direct dimension given from here to here. That's why I probably have to move to the left side because I have to follow the drawings, and whatever dimensions are given into engineering drawing, with that only I have to find my chain. So the next dimension in the chain is from this common surface to the left side surface of the bigger container, which is 20 plus minus 1, and it is negative again. Now once I reach to the left side surface, from there I can directly move to the right side surface, and that's where the dimension 145.0 minus 0.5 plus 2 is going to help me to reach there, and that's why that is my next contributor, and that is seventh contributor. Now this dimension is plus because I am moving from left to right. Once I reach this surface, now from here I can reach to the end point B, and this dimension is exactly same because it is 2 into 20 plus minus 1, and that's why I have shown 8, and this 8 is also going to be negative because right to left is negative. So that is how I started my journey from starting point A. I built a continuous chain. There is no break in between. I pass from one part to other part through common surface, and with this continuous chain, I completed my journey from starting point A to the end point B. So that is how we can build a dimensional chain and assign them positive or negative annotations. Now, the Excel form which we are going to use captures every dimension in its equal bilateral format, and that's why if we have any unequal tolerance, we need to convert that into mean and equal bilateral tolerance, and that is our 8th step. In our example, we have 3 such dimensions and tolerances. Let's convert them into equal bilateral. So the first dimension was 15, 0 plus 1. So how I can convert it into equal bilateral? So we can convert that into equal bilateral by this process. So total tolerance here is 1 mm. As you can see, this 1 mm can be divided into half, that is 0.5. So my tolerance can be plus minus 0.5. Now you have to add this 0.5 into 15. So 15.5 plus minus 0.5 is equal bilateral tolerance. Now you see the upper limit 15 plus 1, which is 16, and you get the same upper limit 15.5 plus 0.5, which is 16. And if you see the lower limit 15, so same limit you are going to get 15.5 minus 0.5 is 15. So that's how this unilateral tolerance is converted into equal bilateral. Same way we have 145 minus 0.5 plus 2. So the total tolerance here is 2.5, and this 2.5 is divided by 2, which is 1.25. So that's how I got plus minus 1.25. Now if I add this 1.25 into lower limit, and lower limit was 145 minus 0.5, which is 144.5, and 144.5 plus 1.25 is 145.75. Very easy to understand. So if you see the lower limit and upper limit here, you'll get the same upper limit and lower limit here. That's how we convert this unequal bilateral tolerance into equal bilateral tolerance. Same way here also. Here total tolerance is 2 mm. So that is plus minus 1 mm. And the lower limit was 18.5 minus 0.5, which was 18. So 18 plus 1 is 19. So that is how we got the mean, right? So every unequal bilateral tolerance or unilateral tolerance is converted into equal bilateral tolerance, and then we replace that here. As you can see, all these tolerances are replaced where I have shown the arrow. Now in the next or ninth step, we are going to use the Excel form and draw the conclusion if we meet our target or not. Now let's understand how to fill this form. So as you see in this, we have ID, which is given for each of the contributor. Now if you go back to this slide, these are the same IDs which are given here. So the same IDs are cascaded here as well. Now this each dimension is shown on a particular drawing, right? So for every container there is a separate drawing. We have bigger container drawing, we have smaller container drawing. So each container will have different drawing numbers. So we have to see which dimension is coming on which drawing. So as you can see that engineering drawing numbers we have to write for each of the dimension. Not only that, where on the drawing your dimension or tolerance is located, because sometimes the engineering drawing can be very complex. It can have many pages. So how to identify that? So P2 means if we divide our entire engineering drawing into multiple blocks. One side you can give the names A, B, C, D, E, F, G like that, and other side you can give the numbers like 1, 2, 3, 4, 5, 6. So if I find out where my dimension is locating, I can very well find one side the letter, other side the number. So P2 means P and 2. Wherever P and 2 lines are crossing each other, that's where I will find my dimension. That is very easy to understand. And -1 means sheet number 1. If it is on the sheet number 2, I will write -2. So very easy. This is going to help me to locate that particular dimension into my engineering drawing. Specifically, it helps in the complex drawing. Now here I have given the description. So the first description is shoulder to right part edge. Okay, shoulder means this shoulder here. So this shoulder to the right part of the edge. So description provides more information about the dimension and tolerance, which will help us to understand that particular dimension and tolerance on the engineering drawing or part. Now here you see I have written the dimension, which is 19. So if you go back here, our first dimension was 19. We had converted that into equal bilateral, and the tolerance was ±1. So as you can see, the 19 dimension is given and the tolerance is ±1. Now here you see we have given positive and negative. So the first dimension, if you go back here, it was negative. So I have to write that particular dimension under negative, and our tolerance is given into plus-minus format. So that is what I have to write. Now you must be understanding now why we had to convert that into plus-minus, because our Excel sheet itself is showing that tolerance into plus-minus format. Okay, that's why we had to convert it. Similarly, we have the second dimension, which is shoulder width, which was 15.5. Again, it was negative, and the tolerance is given here. The third dimension, fourth dimension, fifth dimension, and sixth dimension all were negative. So as you can see here, our first, second, third, fourth, fifth, and sixth, all these dimensions were negative direction, and that's why you find them under the negative column. And now our seventh dimension was positive. So again, if you go back here, 145.75 plus minus 1.25 was positive because we moved from left to right, and that's why it is shown positive here. And our last dimension was also negative, which was same as our sixth dimension. So that is how we got all these dimensions under plus or minus columns and their tolerances. Now we have to add all the dimensions into positive column. That means summation of positive. So summation of positive means there is only one dimension here, 145.75. So I'm just writing that dimension here, 145.75. But in the negative column, there are tons of dimensions, 1, 2, 3, 4, 5, 6 and 7 dimensions. So summation of negative means addition of all these dimensions. So I'm going to get 126.5. Similarly, I have to do summation of all the tolerances. So if I add all these tolerances, I get 6.75. So that is how I got summation of positive, summation of negative and total tolerance here. Now, how to calculate a mean? Now, mean here is not the average. We have to understand it. Mean is the mean gap A dash B. Okay. So with all these dimensions, how we are going to get a mean gap? So mean gap is the difference between summation of positive and summation of negative, because all the dimensions going to the left side versus all the dimensions going to the positive side. And if you take the difference between them, that is what we are going to get as a mean gap between point A and B. So if you do 145.75 minus 126.5, you're going to get mean, which is 19.25. This is a mean gap A dash B, not the average of all the dimensions. Many people get confused here. Now, plus minus tolerance is very easy. You have to directly take this 6.75. Now, maximum limit here is going to be mean plus the tolerance. So 19.25 plus 6.75, which is 26. That is the maximum limit. And the minimum limit here is 19.25 minus 6.75, which is 12.5. That is how I got minimum limit and maximum limit. Now, if you carefully remember, what was the dimension or limit we were interested into? We were interested into minimum limit of the gap. Because if we can fit the maximum size of the container into this minimum limit, then our stack up analysis will work perfectly. Otherwise, we have to do some changes into the container, or we will not be able to fit the fourth container into that gap. So the minimum limit here is 12.5. So that means if we compare the minimum limit here and this minimum limit is at least equivalent to the lower specification limit, which is again equivalent to the maximum size of the container, fourth container. So if it is equivalent or more than this 12.5, this tolerance stack up analysis is perfectly acceptable and we need not do any further changes. But if it was lesser than 12.5, that means we won't be able to fit that fourth container, and that means we have to do something into the other containers. We have to modify something into other containers or big container. So the modification can be the dimensional chain, or the modification can be also the tolerance. So by reducing some of the tolerance, we can reduce the variation here, or we can add or delete some of the dimension to reduce the dimensional chain. By doing these changes into the drawing, we can try to fit that fourth container into the box. But in this case, that is not required because our minimum limit here is 12.5, which is equivalent to the maximum size of our fourth container, which is 12.5. So fourth container can perfectly fit in this gap. Now, stack up analysis, when we add GD&T controls and modifying symbols on the part drawings, become a lot more complex. All the steps which I explained remain the same, but the way we include or exclude some of the dimensions and tolerances and geometrical controls in the chain might differ based upon the GD&T control and modifying symbols. In-depth knowledge of GD&T will help you to interpret and encounter them into your stack-up analysis correctly. So as you studied, stack-up analysis is a very powerful tool in order to verify if our dimensions and tolerances are meeting our actual targets or not. So as you studied, tolerance stack-up analysis is a very powerful tool in order to analyze how the dimensions and tolerances are going to contribute into our target clearances or target function, and we will be able to meet that function or not.